Here's the simplest experiment you can do in your head that already ruins most magnetism explanations. Take a single electric charge, just one. Picture it sitting on a table, perfectly still. Now bring a strong magnet near it. What happens? Nothing. No pull, no push, no drama. And that one fact is like a crowbar under the usual story we tell about magnets. Because if magnetism were just a kind of attraction, or a force field like gravity, it should do something to a lonely charge sitting there. But it doesn't. A magnetic field has zero interest in a charge that isn't moving. So the first question isn't, why do magnets stick to the fridge? The first question is, what is a magnet even interacting with, if it ignores the most basic electric thing in the universe when it's at rest? And once you follow that question honestly, magnetism stops being a bag of tricks and becomes something you can actually see. Most explanations stop at north and south and a picture of curved lines around a bar magnet. Those pictures are not useless. They're just incomplete in a very specific way. They describe where something would happen without telling you what the something is. They're like a weather map with wind arrows but no air. You can memorize the arrows and still have no idea what wind is. What I want to give you is a movie you can run in your mind. A movie that starts with something you can touch and measure and ends with a weird but clean conclusion. Magnetism is not a separate force living in its own box. It's what electricity looks like when motion is involved. Sometimes the motion is obvious, like electrons in a wire. Sometimes it's hidden inside matter. And sometimes it's your motion, because changing how you move changes what you call electric and what you call magnetic. If that sounds like I'm about to hand wave, don't let me. We're going to keep checking Everty. I claim against something you could, at least in principle, measure. Let's begin with the one definition of magnetism that never lies. If we define magnetism by what it does, the rule is brutally specific. The force depends on velocity, and it points sideways. This is the Lorentz force, and even if you've never seen the equation, you've seen the behavior. When a charge moves through a magnetic field, it feels a force that is perpendicular to its motion, not opposite like friction, not toward the magnet like gravity, sideways. That sideways is not a detail. It is the entire personality of magnetism. Here's a way to feel that personality without any math. Imagine you're pushing a shopping cart in a straight line. Now imagine someone keeps applying a force that is always perfectly sideways to your direction of motion. What happens? You don't speed up in the forward direction. Instead, your path curves. You start turning. That is exactly what a magnetic field does to a moving charge. It bends the path. It changes the direction of the velocity, not the speed, at least in the simplest cases where there's no electric field doing work. And that already hints at something deep. Because changing speed means exchanging energy in the obvious way. You speed up, you have more kinetic energy. But if a force is always perpendicular to your velocity, it does no work on you in the usual sense. You can be pushed hard and still not gain speed, just be steered. So magnetism, at the most basic level, is a steering force. Now ask a question that seems too simple to matter. Why does it have to be sideways? Why not forward? Why not backward? Why not toward the magnet? You could shrug and say that's the rule. But if you're trying to actually understand magnetism, shrugging is the beginning of forgetting. We want a picture that makes sideways inevitable. Here's one picture that helps. It's not the final truth of nature, but it's a useful mental machine. Imagine a conveyor belt made of rollers. If you step onto it and walk forward, the rollers can grab your shoes and guide you sideways. The belt's motion and the roller's rotation combine so that your forward movement gets redirected. Your speed might stay about the same, but your direction changes. A magnetic field is not literally rollers in space, but the idea that there is a geometry to the field that turns forward motion into sideways force is closer to reality than north pulls south. The equation compresses that geometry into a cross product, something that is built to produce a perpendicular direction. But don't get hypnotized by the math. The message is magnetism cares about motion and geometry. So if magnetism is a steering effect on moving charge, we can say something precise that is also shocking if you haven't been told it plainly. A magnet cannot pull an electron toward itself in a straight line the way gravity pulls mass, not by magnetic force alone. It can only push sideways relative to the electron's motion. Now you might object, but magnets do pull things toward them. They pull nails. That is, pull paper clips. They pull each other. They even pull that little metal pin inside a compass. Yes, and that's the central mystery. Because if magnetism is sideways and velocity dependent, how do you ever get a net pull toward a magnet? There are two answers, and you need both. First answer, in real materials, there are moving charges everywhere in microscopic ways, and the sideways forces on those motions can produce a macroscopic attraction. Second answer, magnetism is not acting alone. Electric forces and changes in the field arrangement can do the work part, even when the magnetic part is doing the steering. But let's not jump. Let's build the ladder carefully. So if magnets only grab moving charges, a permanent magnet must be full of motion that doesn't look like motion. Pick up a fridge magnet. It feels dead, solid, quiet. Nothing is swirling. Nothing is humming. If you cut it in half, you don't find a tiny battery inside. Yet it produces a magnetic field in the space around it, and that field can steer moving charges and torque compasses and attract certain materials. Where does that field come from? One classic story is, a magnet is like a bunch of tiny current loops. Little loops of moving charge like microscopic wires wrapped in circles. And if you've learned about electromagnets, wrap a wire around a nail, run a current, it becomes magnetic. That story feels plausible. Current makes magnetism, so maybe magnetism in matter is just currents inside. This is not wrong as a first approximation. It's also not the whole truth. Because you can ask a hard question. If a permanent magnet is made of current loops, why don't those currents run down like a battery? Why don't they heat the magnet? Why can a magnet sit on your fridge for years and still be magnetic? In ordinary wires, a current implies charges drifting through a resistive material. That causes heating. It requires a source of energy to keep going. A permanent magnet is not doing that. The motion inside a magnet is not like electrons marching down a wire losing energy. It's closer to electrons being in a state that already has angular momentum and magnetic moment built in. At the atomic level, electrons have two key kinds of motion that matter for magnetism. One is orbital motion. Electrons in atoms have wave-like patterns that correspond to angular momentum and that produces a magnetic moment, like a tiny loop. The other is spin, a quantum property that behaves like an intrinsic angular momentum. It is not literally a little ball spinning, but it has the same mathematical role. It comes with a magnetic moment. Now, if every atom in a piece of iron had random directions of these little magnetic moments, they'd cancel out. You'd have no strong magnet. So the next question becomes, why do some materials line up their atomic magnetic moments instead of canceling? And this is where many explanations either bail out or become mystical. You might hear domains align, and that's true, but it's a label, not a mechanism. Or you might hear quantum, and that's true, but it can become a magic word. Let's keep it concrete. A ferromagnet like iron is made of enormous numbers of atoms, and many of those atoms have unpaired electron spins that give them little magnetic moments. What makes ferromagnets special is that in chunks, these moments tend to align. Those chunks are called domains. Inside a domain, many spins point roughly the same way, so their magnetic effects add instead of cancel. But why would spins prefer to align? Here's the honest answer. It's not because little bar magnets inside are tugging on each other like refrigerator magnets. The magnetic interaction between neighboring atomic moments is actually too weak to explain how strong ferromagnets are at room temperature. The real locking mechanism is quantum mechanical and is called the exchange interaction. That phrase can sound like a spell, so let's translate the idea. In quantum mechanics, electrons are not distinguishable little labeled beads. If you swap two identical electrons, you don't get a different physical situation. The wave function describing them must behave in a specific way under swapping. Combined with the Pauli exclusion principle, this forces electrons to arrange themselves in ways that avoid being in the same state. In certain atoms and solids, the energy ends up lower when neighboring electron spins are aligned, because that alignment allows their spatial wave functions to spread out in a way that reduces electron-electron repulsion. It's a subtle balance of quantum rules and electrostatic energy. Notice what that means. The force that a line spins is not primarily magnetic in the everyday sense. It's a consequence of quantum identity and electric repulsion shaped by the Pauli principle. So magnetism in a permanent magnet is already telling you something. What we call magnetic order is deeply tied to electric interactions and quantum statistics. That's one of the first big perspective shifts. The magnet's strength is not explained by a picture of tiny classical currents alone. You need the quantum locking that makes those moments line up and stay lined up. Now, if the magnet is full of aligned domains, why isn't everything magnetic all the time? Because domains can also arrange themselves so that their fields cancel externally. A piece of iron can have strong domains internally but be unmagnetized overall because the domains point in different directions in different regions. When you magnetize it, you're not creating magnetism from nothing. You're mostly reorienting domains so that more of them point the same way. You're changing the material's internal order. That's hidden motion number one, microscopic magnetic moments locked by quantum rules. But we still haven't answered the original paradox. A magnet doesn't pull on a charge at rest, yet it pulls on iron. So what exactly is it pulling on? It's not pulling on static charge the way an electric field would. It's interacting with the magnetic moments and with the motion of charges inside the material. And because those charges are bound and constrained, sideways forces can translate into macroscopic effects that look like key attraction. Here's a simple analogy. Imagine you have a bunch of tiny wheels on the ground that can spin, and you bring a sideways moving conveyor belt near them. The belt's motion doesn't grab a stationary pebble, but it can grab a wheel because the wheel has a way to convert sideways contact into rolling and a net pull. The structure matters. In iron, the internal electrons and their magnetic moments provide handles for the field. The field reshapes the energy landscape. The system tends toward lower energy states. Domains align with the external field, and the object experiences forces toward regions where the field is stronger. If you've ever seen iron filings jump toward a magnet, that's the story in action. The magnet induces alignment. The alignment creates new field patterns, and the object is pulled into the configuration with lower energy. That brings us to something else most people are never told clearly. Magnetic field lines are not strings that tug things. They are a picture of field direction and strength. The pull is about energy gradients and how the material responds to the field, not about the lines acting like rubber bands. So now we have two pillars. Magnetism is a velocity-dependent sideways force on charges. Permanent magnets have internal magnetic moments aligned by quantum effects, creating a stable magnetic field in space. Good. Now we add the most mind-bending pillar because it's the one that really delivers the way you need to see it. Now for the part that feels like cheating, if you change how you're moving, some magnetic forces turn into plain electric forces. This is not poetry. It's not a metaphor. It's a precise statement of how electromagnetic fields transform between reference frames in special relativity. Here's the seed of the idea. Electric fields come from charges. Magnetic fields come from moving charges, currents. But motion is relative. Moving depends on who is watching. So if magnetic effects depend on motion, and motion depends on your frame, then what you call magnetic versus electric might also depend on your frame. That sounds outrageous until you look at a concrete setup. Imagine a long wire with a steady current. In the lab, you say there are electrons drifting along, and the wire is overall electrically neutral. Positive ions fixed in place, negative electrons moving. You place a stationary positive test charge near the wire. In the lab frame, what happens? The charge is at rest. Magnetic force on a charge at rest is zero. So if anything happens, it would have to be electric. But we usually say the wire is neutral, so there's no electric field from the wire. Therefore, the charge should feel no force at all. Now imagine instead a different test charge that is moving parallel to the wire. In the lab frame, this moving charge does feel a magnetic force due to the wire's magnetic field. It gets pushed toward or away from the wire, depending on direction. So far, this matches standard electromagnetism. Now comes the relativity move. Jump into the frame where the test charge is at rest. From the point of view of that moving charge, the electromagnetism Ends and ions in the wire have different velocities than they did before. And special relativity tells you that lengths contract along the direction of motion for objects moving relative to you. That means the density of charges along the wire, how many positive ions per meter, how many electrons per meter, can look different in this new frame. In one frame, the wire can be neutral. In another frame, it can look slightly charged, and if it looks charged, it produces an electric field, and an electric field can push on a charge at rest. So the force that you called magnetic in the lab frame becomes electric in the moving frame. What changed? Not the physics, just the bookkeeping. Now I want to be careful here because this is exactly where sloppy explanations create confusion. The clean, correct statement is electric and magnetic fields are components of a single electromagnetic field, and when you change inertial frames, the components mix. A field that is purely electric in one frame may have a magnetic component in another, and vice versa. The charge doesn't feel a different universe, it feels the same physical situation, but the split into E and B depends on the observer's motion. So magnetism is not a separate substance. It is partly a relativistic effect of electricity. Does that mean all magnetism is just relativity? Not quite. And this is where we earn the right to say we're showing magnetism the way you need to see it, not the way that wins a short argument. The relativity story explains beautifully why moving charges and currents create magnetic effects and why the force has that sideways geometry. It shows that magnetism and electricity are welded together. But permanent magnets involve quantum mechanics, why electron spins align into domains. Relativity doesn't explain that material property. It explains what the resulting field is and how it behaves in different frames. It doesn't tell you why iron has a strong field and copper doesn't. So the full picture is a three-layer cake. The electromagnetic field is one unified thing. Relativity tells you how its electric and magnetic aspects are related. Charges and currents source that field according to Maxwell's equations. And in matter, quantum mechanics determines what charges and currents are possible as stable internal states, like the aligned spins in ferromagnets. Now let's make the relativity idea feel less like a trick and more like something you could have guessed. Suppose you didn't know any relativity. You just noticed a pattern. Electric forces act on charge, whether the charge is moving or not. Magnetic forces act only when the charge moves, and the direction is perpendicular to motion. If you're a suspicious person, you might say, that sounds like the electric force in a moving coordinate system because when you change coordinate systems, directions mix. A sideways component can appear from something that was forward, depending on how you slice space-time. That's essentially what relativity formalizes. Space and time are not separate in the way your intuition thinks they are. When you change frames, what you call purely spatial and what you call time-like components mix. Electric and magnetic fields are part of the same space-time object. If that feels abstract, anchor it with something simple. Even in everyday life, when you're moving, you measure distances and times differently in practice. You see different Doppler shifts. You see different arrival times. Relativity just makes those differences fundamental and exact. And magnetism is one of the most beautiful everyday places where that exactness shows up. Now let's return to the physical world, because we don't want to get stuck floating in frames. When a magnet pulls a nail, it's not the magnet reaching across the gap. It's the electromagnetic field in the gap doing the pushing. This is the part that changes how you see it. Most people picture forces as something objects do to each other. The magnet pulls the nail pulls the magnet, end of story. But physics, at least modern classical field physics, has a different accounting system that is far more useful. Instead of the magnet pulls the nail across empty space, you say, the magnet creates a field configuration in space. The nail, when placed in that field, changes the configuration. The field has energy stored in it. The system wants to move toward a configuration with lower energy. The result is a force. That sounds like fancy talk, so let's make it tangible. A field is a physical quantity defined at every point in space. For the electromagnetic field, at each point you can talk about an electric field vector and a magnetic field vector. Those vectors can be measured by what force they would exert on test charges. Now, why should you believe the field is real and not just a convenient description? Because the field carries energy. You can calculate how much energy is stored in the electric field between charged plates, for example, and you can observe that changing the field does work, heats things, and moves things. More than that, the field carries momentum. It can push on matter, and matter can push back, and the momentum can reside temporarily in the field itself. That's what resolves the action at a distance discomfort. The magnet is not commanding the nail from afar. The electromagnetic field in the space between them is changing locally, and those local changes transmit stresses and momentum in a way that adds up to a force on the nail. Think of it like tension in a rope. If you pull one end of a rope, the other end moves, but the force is transmitted by the rope itself. The rope has a physical state. The tension is real. In electromagnetism, there is no rope you can hold, but there is a field you can measure, and it plays the same mediating role. Field lines then become like the diagram of tension in the rope. They show direction and relative strength. They are not literal threads. They're a way to visualize how the field is oriented in space. This is also why the phrase magnetic field lines want to contract can be misleading. It's more accurate to say the field has an energy density, and configurations can have lower or higher energy depending on geometry and matum. Ryle response. The system evolves toward lower energy, and the force is the gradient of that energy with respect to position. Now, I'm not asking you to memorize that. I'm asking you to adopt one mental habit. Stop imagining the magnet reaching. Start imagining the space around it in a particular state, and objects move because they respond to that local state. That habit alone makes magnetism feel less like magic. Now we can tie the whole story together in one clean synthesis. Magnetism isn't one thing. It's what you see when hidden motion meets a single electromagnetic field that looks different from different viewpoints. Let me say it again in a way you can test against everything you know. When you see a magnetic effect, somewhere in the story there is motion. Sometimes the motion is obvious, current in a wire, charges moving through a conductor. The magnetic field is then the field associated with moving charge, and it steers other moving charges. Sometimes the motion is hidden in matter, electron spins and orbitals, locked into aligned domains by quantum mechanics. The material sustains a magnetic field not by a draining current, but by being in a stable, quantum-ordered state. And sometimes the motion is you. When you change inertial frames, you change what counts as electric field versus magnetic field. A force that is magnetic in one frame can be electric in another. That's not a trick. It's a clue that E and B are not separate entities. So what is magnetism finally, if you want one sentence that isn't a lie? Magnetism is the manifestation of the electromagnetic field associated with moving charge and changing electric fields, and it acts on moving charges in a way that is fundamentally tied to the geometry of space-time. That's still a mouthful, but now it's a mouthful you can unpack. You can unpack it into Lorentz force behavior. You can unpack it into Maxwell's equations about sources. You can unpack it into relativity's transformation rules. And you can unpack it into quantum mechanics of matter that produces stable magnetic moments. Now, since this video title promised the way you need to see it, let's end by giving you one concrete lens you can carry into ordinary life. The next time you watch a magnet snap to steel, try this thought. You're watching space itself settle into a new shape, and the objects just follow the geometry. That's not mystical. It's a precise idea. The electromagnetic field in the region is changing, the energy stored in that field is changing, and the system moves toward the configuration that lowers the total energy. If you want to go one step further, here's a question you can keep as a hook for the next chapter. If changing motion can turn electric into magnetic, and changing electric fields can create magnetic fields, what happens when fields change fast enough that the changes themselves propagate through space? That question leads to induction, to electromagnetic waves, and to the fact that light is an electromagnetic phenomenon. So magnetism is not a side topic. It's one face of the thing that light. Rally lets you see. And now, When someone shows you a drawing of field lines and says north and south, you can appreciate the drawing and also know what's missing. You'll ask, where is the motion, and what frame are we in, and what is the field doing in the space between? Because that is magnetism the way you need to see it.